Welcome to this explainer. Okay, if you're a junior developer staring down a massive modern Kotlin full-stack project for the very first time, just take a deep breath. You are exactly where you need to be. My goal today is to help you build an intuitive, rock-solid mental model of this entire codebase. We're going to be doing a detailed term-by-term walkthrough of the core glossary, specifically from sections 33 and 34 of our source material. We're mapping out the territory layer by layer. That way, when you sit down to write your first real feature, you'll know exactly where things go and, more importantly, why. So let's dive right in.
Here's our agenda for today. We'll start with Kotlin and OOP foundations, then move into architecture and patterns. After that, we'll hit the backend and HTTP, drop down into persistence, and finally wrap up with Android and Compose UI.
Starting off with Section 1, Kotlin and OOP foundations, the building blocks.
So, right out of the gate, Kotlin kind of flips our assumptions about equality compared to older languages. In Kotlin, the double equals sign represents structural equality. You can think of it as a field-by-field audit. Under the hood, it automatically calls the equals method to see if the actual contents perfectly match. On the flip side, the triple equals sign is our referential equality. This acts more like a strict memory auditor. It checks if two references are pointing to the exact same physical space in ramp. So for value objects where equality strictly means the same fields, we use structural equality. But for our database entities, we can use referential shortcuts, because if it's literally the same object in memory, we can entirely skip the expensive process of comparing every single field.
Now, let's look at a literal language superpower, the smart cast. In older languages, checking a type means you still have to manually cast it on the very next line, right? It's redundant, it's noisy. Well, Kotlin's compiler is smarter. Once you verify an object is of a particular type, or maybe just verify that it isn't null, the compiler essentially locks that knowledge in. It automatically narrows the variable's type for the rest of that scope. No more writing explicit, messy casts everywhere. If you verify an object as an entity, on the very next line, you just call a property on it and it works. The compiler confidently remembers the check, which saves us just a massive amount of boilerplate.
Listen to this fantastic piece of senior developer wisdom straight from the glossary. I default to val everywhere because it's the immutability principle enforced at the language level. var is the exception. The core object-oriented programming principle at play here is immutability. Reading code is simply faster and honestly infinitely less bug-prone when you know variables won't just magically mutate halfway through a function. Every single property on our domain entities is declared as a val, meaning value, meaning read-only. It makes navigating this codebase totally predictable.
Moving right along to Section 2, architecture and patterns, the blueprint.
The absolute golden rule of clean architecture is surprisingly simple. Dependencies must point inward. Think of the app like a fortress. The inner keep is our domain layer. It holds the pure business logic, and it is completely sacred. It imports zero framework details. No web servers, no database libraries, nothing. The outer walls, like the data layer for persistence and the API layer for the web, wrap around the domain and point inwards toward it. They depend on the domain, but the domain depends on absolutely nothing. And because of those incredibly strict boundaries, we end up with three distinct glossary terms for the shapes our data takes. First, the DTO, or data transfer object. This is strictly shaped for the network wire. It's raw JSON in, JSON out with zero business rules attached. Next, we have the domain entity. This is your core business object. It's packed with complex behaviors, validations, and invariants that absolutely cannot be violated. Finally, the database entity. This one is shaped exclusively for the object relational mapper as a mutable row in a database table. By enforcing these three distinct shapes, we literally guarantee that malicious or malformed JSON from the web can never, ever bypass our core business rules.
So how do we pull this off? By utilizing the repository pattern and dependency injection. This is where we pass dependencies into a class rather than hard-coding them inside. It completely abstracts our data access behind clean interfaces. The domain layer just says, hey, I need to save this user. It doesn't know, and frankly doesn't care, if that user is being saved in a lightweight, in-memory test database or a heavy Postgres production database. We can effortlessly swap out those database implementations without touching a single line of our sacred business logic.
Okay, Section 3, the backend and HTTP, exposing the domain.
You might be wondering, how does Ktor manage to be so incredibly fast and memory efficient? The secret term here is the coroutine. Think of a coroutine as a highly lightweight, suspendable computation. Unlike traditional server architectures that block an entire operating system thread while waiting for a slow database query to return, a coroutine just suspends. It pauses. The underlying thread is instantly freed up, and it immediately picks up another incoming network request. This is exactly how we handle thousands upon thousands of concurrent requests without eating up gigabytes of server memory. When we actually expose our data, we adhere strictly to REST semantics, utilizing standardized HTTP status codes as our universal language. If our pure domain throws an illegal argument exception because a strict business rule was broken, we instantly translate that to a 400 bad request. If the domain throws a no such element exception, boom, we return a standard 404 not found. Standardizing these status codes prevents massive integration headaches for the client applications that are consuming our API. But the real magic trick is how we achieve that translation without cluttering up our code base. Ktor features this incredibly elegant plugin called StatusPages. Instead of wrapping every single route handler in massive, messy try-catch blocks, we centralize the error handling globally. Our domain entities just throw normal exceptions when a rule is violated, and the StatusPages plugin gracefully catches them at the edge of the application, seamlessly translating them into the proper HTTP response. It keeps our routing code remarkably clean and focused solely on just handling requests.
Section 4. Persistence and databases. Saving state.
The absolute bedrock of our persistence layer is the database transaction. In glossary terms, a transaction is an atomic unit of work. Every single repository method that touches the database is wrapped in a dedicated transaction block. This is absolutely crucial because it guarantees that if we're writing a new observation, updating a user profile, and logging an analytics event, and that third step suddenly fails, the first two steps are instantly rolled back. No partial data. No ghosts in the machine. We never, ever leave our database in a corrupted, half-written state. For our framework of choice here, we go with JetBrains Exposed. It heavily favors a DSL, a domain-specific language, over heavy, traditional, object-relational mappers like JPA. What this means is your SQL queries are written natively as type-safe Kotlin code. Misspelled column names, mismatched data types, they are caught immediately at compile time, long before the code ever actually runs. Because let's be real, explicit always beats magical when you're deeply debugging a failing query. We want to see exactly what our SQL is executing under the hood, without any hidden proxies or lazy loading surprises.
Finally, Section 5. Android and Compose. The UI layer. Modern Android relies heavily on the MVVM, Model View View Model architecture, paired natively with Jetpack Compose. This creates a beautifully reactive one-way data flow. Here is how it works. First, the view model grabs fresh data from our repositories and updates a state flow. Second, that exact state change triggers what we call a recomposition. The UI framework realizes the underlying data has changed and flags the screen for an update. And third, the composable function essentially repaints itself from scratch using the new state. The UI is quite literally just a mathematical function of the state.
Let's unpack stateflow for a second. In our glossary of reactive programming, stateflow is what we call a hot flow, specifically designed for observable state. Crucially, it inherently conflates duplicates. If you set the exact same state value twice in a row, it only fires one single update to the UI. Contrast this with shared flow, which is used for one-off events like a navigation click or a toast message. Stateflow's built-in deduplication is a total lifesaver. It prevents highly expensive, redundant UI redraws when a user does something simple like, say, rotating their phone screen.
Now, to ensure our UI components aren't a complete nightmare to test and reuse, we utilize a vital technique known as state hoisting. Literally, we hoist or lift the state out of a local composable widget and move it up to its parent caller. So instead of a text field heavily managing its own internal text variable, it simply receives the text as a parameter and fires a callback event when the user types a new character. This is a game changer. It transforms our composables into pure, predictable functions. Data goes in, UI comes out, rather than tangled webs of hidden, untestable local variables.
And the unsung hero holding all that hoisted state? The view model. The view model has some serious superpowers in the Android ecosystem. It automatically survives configuration changes, meaning if you rotate your phone, your data isn't abruptly destroyed. It holds a single immutable UI state data class, so the screen always has one reliable source of truth. And it safely launches asynchronous coroutines in its dedicated scope. This ensures that background network requests are cleanly canceled exactly when the user navigates away from the screen. I want to leave you with this final piece of mentorship advice from the source guide as you transition into Compose. If you're coming from legacy XML layouts, this is the mental leap you absolutely need to make. Building UI is no longer about inflating static imperative layout files. It fundamentally becomes composing functions.
You just write a lightweight function that declares what the UI should look like for a given piece of state, and the Composed framework handles the rest. Well, we've traveled all the way from a basic val declaration, straight through the pristine domain boundaries, across the HTTP network, down into the atomic database transactions, and all the way back up to the reactive Compose UI. You now have a rock-solid mental model of this entire full-stack architecture. The only question left is, you know the layers, now what will you build with them? Grab a ticket, dive into the code, and start exploring.